Hey guys, this video is going to be a continuation of the last video where we're learning about new sets of trig identities. This video is going to cover double angle formulas and power reducing formulas. I want to start with these double angle formulas and actually prove where they come from using previous identities that we've seen. So in the last video, for instance, we saw that sine of u plus v was this identity. It was sine of u times cosine of v plus cosine of u times sine of v. And the reason I'm highlighting this one from last time is that this first identity says sine of 2 theta. So if I rewrote sine of 2 theta as theta plus theta, this starts to look a lot like this. It's just we don't have two different angles, u and v. We have two of the same angle, theta and theta. But we can still use this format to expand out what this would be. So it starts with sine of u times cosine of v. In other words, sine of the first angle, so sine of theta, times cosine of the second angle, which is also theta, plus cosine of the first angle, which is theta, times sine of the second angle, which is again theta. So here we have two terms. We've got sine times cosine and cosine times sine. And both terms have the same things just being multiplied together in different orders. That order doesn't matter, so I can actually put these together and just call it 2 times the sine of theta times the cosine of theta. And that's this first identity. We have sine of 2 theta equals 2 times sine times cosine. And if I had to pick one of these that's probably the most important, I would say it's this one. It'll come up a bit this year, but it'll come up a lot next year in calc. Let's do the same thing quickly for cosine of 2 theta. So I'm going to use the identity from last time that said cosine of u plus v equals, and then it was cosine of u times cosine of v minus sine of u times sine of v. But again, this identity has cosine of 2 theta, so I'm going to take that 2 theta and separate it into theta plus theta, so that my two angles u and v both become the same thing, theta and theta. So this would say cosine of theta times, well, cosine of the second angle is also theta, minus, and then again, sine of theta times sine of theta. And these are the same trig terms multiplied together, so we'll say that's cosine squared theta minus sine squared theta. So that's where this first one comes from, but there's two more. It's kind of weird that they show us three different identities for cosine of 2 theta, but here's why they do that. If you remember back to one of the Pythagorean identities, we know that sine squared of theta plus cosine squared of theta equals 1. So I'm going to use this identity to substitute something in for cosine squared or sine squared. So over here, I want to change cosine squared. Okay, so if I were to take the sine squared and move it over to the other side, this would say cosine squared equals 1 minus sine squared. So I'll replace this with 1 minus sine squared, but then we still have minus sine squared. And that's how when you simplify that, you end up with 1 minus 2 times the sine squared of theta. And that's actually this bottom one. So now I'm going to go over here and change the sine squared into something. So I'll start with just the cosine squared from the beginning, minus, but then I'm going to change sine squared. So if I were to keep this where it is, and then move cosine squared over here, it'd say 1 minus cosine squared. So sine squared is 1 minus cosine squared. And now I just have to simplify this. So distributing the negative 1 in would make this a negative 1 and a positive cosine squared. So if I have two of these positive cosine squareds, I'll write that out. 2 cosine squared minus 1. And that's that second identity. So these are all saying the same thing. They're kind of interchangeable. It's just sometimes one will be more useful than the other, depending on if we want to work with both cosine and sine, or just cosine, or just sine. And in the interest of time, I'm not going to do the same thing with tangent, but we could prove this identity, again, using tangent of u plus v from the last video. So let's see how we can actually use these in some examples. In these problems, it says to use the figure to find the exact value of the trig function. So first, if we look at this triangle, I notice that I have two of the sides labeled. We have 3 and 4, and this is supposed to be a right triangle. And I notice right away that the hypotenuse should be 5. This is a Pythagorean triple, and if you don't recognize that, you could still just get the hypotenuse using the Pythagorean theorem. And it's helpful to have all of the side lengths because now we're going to be evaluating this. So sine of 2 theta, we just saw that that identity said 2 times sine of theta times cosine of theta. And this angle theta that we're talking about is right here. So the sine of that angle theta would be opposite over hypotenuse, so 3 over 5, so 3/5. Don't forget to keep the 2 out front, so 2 times and then 3/5, and then the cosine value. So cosine is adjacent over hypotenuse, so that would be 4 over 5. And now we just have an expression that we need to simplify. So I'm going to multiply these fractions together first. So I'll leave the 2 out front, and 3 times 4 on top would be 12, and we'd have 25 on bottom. And then when I multiply that by 2, I'm really just multiplying the top by 2, so 24 over 25. For cosine of 2 theta, we have 3 options, and it doesn't really matter which one we pick here because I know the sine and cosine values, so I'm just going to go with the first one, which said cosine squared minus sine squared. Again, the cosine value on this triangle is 4/5. We're squaring that, and then subtract the sine value, which was 3/5. So if I square the first fraction, we'd have 16/25, and then we're subtracting 9/25, and 16 minus 9 is 7, so 7/25. Now, tangent of 2 theta, that was the fraction one. So if you look back at those identities, that was 2 times the tangent of theta over 1 minus tangent squared. Now that I have this identity set up, we can just start filling in these values from the table. Okay, so again, we have 2 times tangent on top. So the tangent was, let's see, tangent is opposite over adjacent, so 3/4. So we have 2 times 3/4 over, and then 1 minus that tangent value squared. So I'll work on simplifying the numerator first. We have this 2 that will cancel out part of this 4 on bottom and make that a 2. So we have 3/2 on top. And then on bottom, let's see, this fraction, when I square that, that would be 9/16. Okay, so we're taking 1 minus 9/16. Well, this is like 16/16. So again, 16 minus 9 is 7. So this is all over 7/16. And then the last thing I'll do is just change that to multiplying by the reciprocal of the bottom. So 3/2 times 16 over 7. The 2 and the 16 can simplify. That'll become an 8. And then we have 3 times 8, which is 24, over 7. Now the last one is cosecant of 2 theta, and we don't have an identity or a formula for that. But we do know the sine value, the sine of 2 theta, was 24 over 25. So if I just take the reciprocal, that would make this one 25 over 24. And I'll leave this one in a different color just because we didn't do it like the last problems, like we didn't use an identity, we just took the sine of 2 theta value and reciprocated it. So before we move on, let's actually take a step back and see what we were really doing here. Like in number 2, we had cosine of 2 theta. So that's like saying, let's take our angle theta and multiply it by 2. So if I took this acute angle and just made it twice as big, it would look something like that. So then your right triangle might look something more like this. And as I'm just sketching this out, I'm trying to keep the hypotenuse the same because we're thinking of these triangles as like coming from the unit circle kind of. I know this hypotenuse is technically 5, but that's how you have to think of these triangles as being related. So as this angle gets twice as big, we can't just say that the cosine value doubles. Originally it was 4 over 5, and when we make this new triangle, the cosine value is actually smaller than it originally was. So basically what I'm getting at here is we can't say that this is the same thing as just 2 times the cosine of theta. And that's why we have to use these identities instead. All right, here are similar problems. We're just not given a triangle to start with. Instead, it tells us that the tangent of theta is 1/2, and then this little statement says pi is less than theta is less than 3 pi over 2. Which is confusing if you just read it from left to right. The way I think of it is theta is somewhere between pi and 3 pi over 2. So let's draw the situation out first. It said our angle theta is somewhere between pi and 3 pi over 2. So that just tells me that it's got to be somewhere over here in the third quadrant. And then it tells me that the tangent value is 1/2. So opposite over adjacent would be 1/2. But actually on the unit circle, this would be like a negative since it's going down, and this would be a negative since it's going to the left. So -1 over -2 is still positive 1/2, so that works. Now this is not one of our special triangles that we're used to seeing, but we can use the Pythagorean theorem and figure out the hypotenuse length. So if we have 1 squared plus 2 squared equals, and then c squared, we'd have 1 plus 4 is c squared. So the hypotenuse would be the square root of 5. So now that we have this drawn out, we know what our triangle looks like. We can just start filling in values in these problems. So again, sine of 2 theta was 2 times the sine of theta times the cosine of theta. So again, keep the 2 in front, and then the sine value is opposite over hypotenuse, so -1 over the square root of 5. And then the cosine value would be -2 over the square root of 5. So when we multiply these together, I'll do the fractions first. The negatives will cancel out, and we'd be left with on top 1 times 2, and on bottom the square root of 5 times itself is just 5. And then when you multiply both of these 2's together, you would just get 4 over 5. So that's the sine of 2 theta. Cosine of 2 theta, again, I'm just going to default to using that cosine squared minus sine squared. So the cosine value we said was -2 over the square root of 5. Just careful because we have to square that. And then subtract the sine value, which was -1 over the square root of 5. Again, being squared. Squaring the first fraction would give me 4 over 5. Squaring the second fraction would just give me 1 over 5. And when I subtract 4/5 minus 1/5, I just get 3/5. So it's kind of weird that so far we're dealing with these more complicated trig identities, and this isn't even a special triangle, so it's not like the nicest values. We have that square root of 5 in there, But so far, both of these ending values have worked out to be pretty nice, 4/5 and 3/5. Let's see what we get for tangent of 2 theta. Again, that formula was 2 times the tangent of theta over 1 minus tangent squared. And they actually told us the tangent value. We don't even have to look at the triangle. We know it's 1/2. So 2 times 1/2 on top, and then over 1 minus 1/2 squared. So 2 times 1/2 on top is just 1, and then 1/2 squared would be 1/4. So 1 minus 1/4 would be 3/4. And 1 divided by 3/4 is the same as 4/3. So our final answer is just 4/3. So that one worked out pretty nice too. To end the video, we're going to talk about these power reducing formulas and just go through 2 proof examples. So power reducing formulas do exactly what you'd think they would. They take something like sine squared, here the power is the squared, and it reduces it. So if you see here, we don't have anything being squared anymore. And that can definitely help us to simplify something down. Now I know this is technically a more complicated looking expression, but at least it's not being squared anymore. So let's see what we can do in these examples. It says verify the identity algebraically, which is just fancy math directions for saying prove this. In this first example, we have cosine to the fourth minus sine to the fourth equals cosine of 2 theta. And that doesn't seem like a very believable statement. Like we actually just saw that cosine of 2 theta equals cosine squared minus sine squared. So it's kind of weird if someone came up to you and told you that cosine of 2 theta actually equals cosine to the fourth minus sine to the fourth. But it is true, and we can try to prove it. So the thing with these proofs is there's often a few different ways that you can handle them. So the way that I do it is not necessarily the right or the best way, because there is no necessarily right or best way of doing it. But there are a couple general guidelines that you can follow that will help you. And one of those would be anytime you can factor something, maybe try that. So cosine to the fourth minus sine to the fourth is actually a difference of squares. I could factor that into cosine squared minus sine squared and cosine squared plus sine squared. And then on the right, I'll just leave the cosine of 2 theta. Now it's important when you do these proofs that you only work on one side. I chose to work on the left side just because that seemed like the more complicated thing. Like cosine to the fourth minus sine to the fourth seemed like something I could actually manipulate. Cosine of 2 theta seemed pretty simple already. So I'm working on the left side, and I'm always going to leave this right side alone. I'll know the proof is done because at the end it'll say cosine of 2 theta equals cosine of 2 theta. That's how I'll know when I'm done. So anyways, all of that to say, here's our first step. Let's just continue to work on just the left side. And so what can we do over here? We've got cosine squared minus sine squared. That's good. That's actually what cosine of 2 theta is. So I want to hold on to this. But then I notice that I have this stuff, cosine squared plus sine squared, and I need to get rid of that. And actually that's the Pythagorean identity. That just equals 1. So I can just substitute everything in those parentheses for just 1. And that's how we end up with just cosine squared minus sine squared equals cosine of 2 theta. Now we're not technically done yet. I know it kind of feels like we are because this is one of our identities. You can see it on your identity sheet that this is true. But in order to completely prove something, you do need your last statement to be something equals itself. So my last step is just going to be to say that cosine squared minus sine squared equals cosine of 2 theta. So then we have cosine of 2 theta equals cosine of 2 theta. Basically, when you're proving something, think about like you need to end it with a statement that is so irrefutably true that like no one could argue it. Like up here, maybe someone doesn't know their trig identities and then they wouldn't know that this is true. So you don't want to end your proof there. You'd want to end it here because cosine of 2 theta has to equal cosine of 2 theta. You don't need to know much trig to understand that that's true. So that was actually kind of an easy just 2-step proof. Let's see what we can do with number 2. The first thing I really need to decide is what side am I going to work on? Like, do I want to simplify this side or do I want to simplify the right side? And again, there's multiple ways of doing these problems, so you could probably make arguments for both. I'm going to try to work on the right side, just because we've got this squared thing here and we have all these power reducing formulas available to us. So I'm going to leave the left side how it is, 1 plus cosine of 10x. But on the right side, I'm going to use a power reducing formula on this. Okay, so I'll leave the 2 where it's at, and then cosine squared of 5x. All right, so we've got cosine, so it's going to change into this stuff. Now notice that this angle was originally theta, and it changed to be 2 theta. So in our problem, we're starting with 5x. Okay, so if you notice how the angle is basically doubling here, instead of having 5x, I'm going to write 10x here. So I'll start writing this out because we have this fraction. We've got 1 plus cosine of 2 theta, but in this case it's cosine of 10x over, and then just this 2. So just one more time real quick. We had 5x to begin with, and that's kind of like in the power reducing formula we had theta. And then the formula tells us that we have to double the angle theta, which means we have to double the 5x and make it a 10x. But now that we've made this big substitution, we can just start simplifying things down. Okay, so we have 2 out front, and then dividing by 2 in here, those will go away, and we're left with just 1 plus cosine of 10x. And that's actually what we have on the left side. So again, this is just an easy 2-step proof. And now that the left and the right side are exactly the same, we can say that we're done. Hopefully that will get you started with your double angle and power reducing formulas.